and welcome to another physics tutorial. Today we'll be talking about motion and specifically, we'll be talking about forces and specifically a tension force system in which we're asked to find certain properties about the system. So let's jump right in. The figure below shows an arrangement in which four disks are suspended by cords. The longer top cord loops over a frictionless pulley and pulls with a force of magnitude 88 newtons on the wall to which it is attached. The tensions in the shorter cords are T1 is 52 newtons, T2 is 44.2 newtons, and T3 is 7.8 newtons. And so, although it's not written above, the question asks what are the masses of each of the disks. And you can see the disks labeled in the picture there, A, B, C, D. So that's what we're trying to find. We're trying to find the masses of those disks. And we can effectively do that because we are given we're given each of the tension forces in each of the components, and we're also given the tension force of the entire system on the wall. And I've labeled them there on a diagram for clarity and just to save time. And so, all right, let's get started. So the way I like to approach these sorts of problems is to split it up into independent systems and then reevaluate the system analytically. So first, let's take a look at mass D. Okay, so mass D. And instead of writing the parts, what I'll do is I'll write the mass. So this is mass D. Okay, so mass D is, let's take a look. So if we split the system up independently, what we get is we get the tension force of T3, and this is a very crude drawing, but here's the mass of D, and then we get another force going down, which is gravity. Fg, gravity times the mass. And so, essentially what we can do here is set up an equation using Newton's equations. We know that because the system is stable, that Fg of D, of this component, is equivalent to T3, which is 7.8 newtons. 7.8 newtons. Additionally, we can decompose this to write that the mass of D times gravity is equal to 7.8 newtons. And solving for the mass of D, we get mass D is equal to about 0.796 kilograms. And there we have it. There is the mass of D. All right. So now we can look at C. And so component C is attached to, you've got T2, and then you've got the mass of C, and then you've got T3, you've got D. So this system is, if you can picture this, we have, here's here's T2, here's the mass of C, and then here is T3 and the mass D. So in this system, we have this T2 force, which we're going to set up an equation much like this. And we have this T2 force here, and the mass C. And then in addition to a gravitational force on C, we also have 7.8 newtons of tension this way, which is acting down on C. So this time our equation of motion is going to be force equation is going to be that T2 is equal to Fg of C plus 7.8. And decomposing this, we get 44.2 is equal to mass of C times gravity plus 7.8. And using algebra, that's 36.4 equal to 9.8 times the mass of C. And then we get that the mass of C is equal to about 3.71 kilograms. And there it is. That's all there is to it. All right, great. So now let's move on to the mass B. And you'll notice that I find it easier in this situation with these masses and the tension to work upwards because it's easier as you find these masses, and picturing it is just easier in my opinion. So that's what I like to do. All right, so let's look at mass B. So in mass B, we have the mass B, and we have a force upwards, T1. This is T1. And then we also have force downwards, which is T2. So in this system, once again, like we saw over here, we've got T1, the force pulling up, tension force upwards. We've got the mass B, which is also subject to Fg, force of gravity. And we also have a tension force because of these masses, the additional masses downwards. So in writing this equation, we're going to have to factor in that. And what we get is that T1 is equal to T2 plus FGB. And then plugging in values, that is 52.0 is equal to 44.2 plus FGB. And subtracting them, that's 7.8 is equal to the mass of B times 9.8. And we get that the mass of B is roughly, sorry about that. The mass of B is roughly, let me do the calculation quickly, 0.7959 kilograms. Okay, there it is. So that's B. So the last mass we have to find is mass A. And finding mass A, we need to consider the overall tension. So the tension on the wall. And because, as we know from Newton's third law, each reaction has an opposite action, the tension, the wall's displacement of the tension is equivalent to 88 newtons throughout the system. So we can say that the tension force here, because it's the string we're assuming is not elastic, we can draw a diagram such that this force upwards is 88, or as I drew in the diagram, it's T naught on the mass A, and then downwards we have 52 0 newtons, or T1, which is holding up all the others. So 52 accounts for all of the others in this sense. And we just solve this simply by doing and we also have to consider, remember, Fg of A. So we solve this by setting 88 newtons equal to, sorry, that doesn't look very good, 88 newtons is equal to 52 newtons plus FGA, and then we get 36 is equal to the mass of A times gravity, and where gravity is equal to 9.8, we get that the mass of A is equal to about 3.673 kilograms. And there it is. That's all there is to this tension force system. It's relatively simple in practice. Solving the equations is just algebra. But sometimes the concepts get tricky, and I know myself, I get tripped up with this a little bit. So I hope this was helpful to you, and hope to see you next time. Thanks.